Hi, this is a presentation of the operation of EIGRP. EIGRP performs neighbor adjacency, which means that it will keep track of its neighbors by sending out small hello packages to see, is anyone there? And then you'd send back that, oh yes, I'm here, and here are my routing information. And then it sends out every 5 seconds a hello packet to keep track of them. When they receive router information from their neighbors, the routers will create a topology table. And that's information about their neighbors and the routes that they are connected to, or the networks that they are connected to. So they keep their EIGRP topology table updated, and if there is a change in this table, it will send an update to its neighbors and say, now there has been a change, and what the change is. When this change has propagated all through the network and everyone has updated their topology table and therefore also the routing table, well, then we have a convergence in our network. Then all routers have the correct, most up-to-date information about all the network that is convergence. The EIGRP uses a composite metric. It doesn't only look at, for instance, as RIP does, look at the hop count, or like OSPF that uses the bandwidth as the cost. Here we have different a formula that will calculate the metric. And it has 5 different constants that we can set either to 1 or 0, depending on how we want to calculate the metric. By default, K1 and K3, which is the bandwidth, and the delay are set to 1, which is those two that we use when we calculate the metric. It could also be load, for instance, which is K2, and K4 and K5, which are reliability of the link. Both the bandwidth and the delay are static values. It's not the actual, it doesn't measure the bandwidth or the delay. There is a preset number for both the bandwidth and the delay. The bandwidth, for instance, can be put in ourselves. The bandwidth is in kilobits per second. The delay is in microseconds. The reliability is not included in the basic setup. You can, of course, put it in. And the TX load and the RX load, the transmit and the receive load, is not either a part of it. These two, the reliability and the TX and RX load, are actually things that are measured dynamically. So if I want to set and change the bandwidth, I can do that with the bandwidth command. Of course, if I have a fast Ethernet interface, the bandwidth is 100 megabit. If I have a gigabit, it's 1 gigabit. If it's a 10 megabit Ethernet, well, then it's 10 megabit. So, and that is the bandwidth. But of course, there are some other interfaces, for instance, the serial interfaces, where the bandwidth can be different. And by default, most serial links have a bandwidth set to 1.544 kilobit per second. And I can change that by using the bandwidth command or by using the clock rate command. The delay values here for normal 10 megabit Ethernet, the delay is set to 1, fast Ethernet to 100, gigabit to 10, the normal Ethernet is set to 1000, and token ring and other types of networks here have a pre-configured delay metric. So when it calculates the metric, it looks at the slowest bandwidth overall and take that and take 10 million and divide it by the bandwidth. Then it takes and adds the delay and divide it by 10. Then it multiplies the sum with 256. Then we get the metric. And the metric, as you can see here, it's a large number. Here it's 3012096, which is a huge number. So that is the bandwidth when I've calculated here by the standard method. And of course, it will always try to choose the one with the lowest metric. Then, when I have the metrics calculated, well then I use the diffusing update algorithm, the dual, to find a loop-free and a loop-free backup path. A loop-free path and a loop-free backup path. And this here ensures us with a fast convergence because we already calculate the best path, but also the backup path if it's possible. Well, it's not always possible, and that's included in the dual. So it doesn't have to calculate it every time there is a change. If something goes down, it will just look at, do I have a backup? And then it will choose that. If it doesn't have it, then it has to do the dual algorithm once more. That ensures us that we have actually fast convergence. And also that we doesn't use the bandwidth for setting up routing updates all the time. So the dual finite state machine, FSM, keeps track of all the routes. And we will look into that because there are also some other things that we need to know what is. For instance, there is something called a successor. That is actually the via address. This is which route, which way will I go when I want to go to a network. And that is the fastest one. And the feasible distance is actually the metric. That is the lowest calculated metric to reach this network. So this is what I will find in my routing table. The feasible distance and the successor to a network. So that is the successor. Then we can have a feasible successor. A feasible successor is a backup path. If something happens to the successor, then automatically the feasible successor will take over. And how do I become a feasible successor? Well, then I need to meet a requirement called the feasibility condition, which means that if the reported distance of a network is less than the router's feasible distance to the same network, then this will be a feasible successor. If it's higher, then it will not. This is because I want to make sure that this is a loop-free environment. And and the reported distance is the neighbor's feasible distance to the same destination network. So I need to look at actually the metrics for these two and see if the one that is supposed to be the feasible successor, if that has a lower metric than myself, which actually means that it is closer to the destination network than myself. So, and how can we see that? Well, we can see that if we go into the topology table with the show IP EIGRP topology. Then we will see the different networks. We will see that if we have a successor, of course, we will have that, and if we have a feasible successor as well. And we can see that if we go into the different lines here and see that we have a feasible distance of a router, and if I want to have a successor, I want to have a feasible successor, then I'll look at the feasible distance and see that this is lower than the router's own feasible distance. For instance, here, if I have the example over here where I have a feasible distance, which is 301,296, no, I don't know, 3,120,096, and then this one here is lower. It's 2 million something. 1, 2, 3, yeah, 2 million something. So it's lower. So this will be a feasible successor. Over here, I have with the feasible distance here is 2 million something, and the reported distance here of my successor is 3 million something, and then this is higher, and that will not become a feasible successor. So this is how it's calculated, but of course this is something that the dual algorithm will take care of by itself. So you don't really need to do anything. So this is the finite state machine, which is how the dual is working. I don't want to go into that. Yeah. So, and you can debug this. If you want to look into what's actually happening here, you can go in and see debug EIGRP FSM for the finite state machine, and then you can see all the updates come and going, and how to set it up. If you do a show IP EIGRP topology, and it's a P in front of the line, which means that this here is passive, which is actually meaning that it is working. If it's an A, it means that the dual algorithm is active and that it's actually calculating a new successor and a feasible successor. So P is up and running, and no change is applying. Yeah, and that was it. Thank you.